Good morning, everyone. Today is October 21st, 2017, and this is the John Chappell Natural Philosophy Society Morning Science Chat. I am your moderator, Franklin Hu, and this webinar is being brought to you by, of course, the John Chappell Natural Philosophy Society. We have our website that you can visit. And if you haven't already, please renew your membership. And we often have discussions in our forums and through email. And we're also on Facebook. So give us a like and please participate in our activities, including this Saturday Science Chat. So today we have a special guest, MV Mohanlal. Am I pronouncing your name correctly? Let's see here. Let me unmute you there.
Mohanlal H V.
So it's great to have you here. And you're in India?
Yeah, I'm in Bangalore, India.
Bangalore, India. Well, thank you for joining us from so far away.
Thank you, sir. Thank you. It's my pleasure.
All right. So initially, we had discussed, how long you've been working on this.
This is approximately 4 years. Past 4 years I've been working on this.
That's a remarkable body of work for only 4 years. I think I've been working on my stuff for like 13 years. I got nothing like what you've got. All right. So would you like to kick off the discussion? How would you like to go? I know that you've provided us with 3 videos on 3 different topics. I suggest we start with one of them and see how it goes.
So I think I would like to start with the moon, whether it is rotating or not. That's a big mystery, no? We cannot see all the sides of the moon. Even then, mainstream physicists, astrophysicists say that the moon rotates once in a single orbit. So the videos that I have presented, there we can see, on purpose I made it 4, 3, 2 and 1 rotation because we can see a rotating moon, how it rotates. So I brought it down to 4, 3, 2 and 1 rotation. That single rotation we can easily make out that it is rotating once. So there can be only one rotation in the anti-clockwise direction. Either what I have shown should be correct or what the mainstream physicists are telling that should be correct. So only either one of them can be correct. So which one is correct? That we have to decide.
All right. Well, maybe we could show that piece of the video so that people would know what that's about. And then open that up for questions. Okay, so I'm going to see if I can find that part where you show that. Okay, I think I found it. Okay. So I'm going to go like that. Then I'm going to... See, that definitely sounded like someone was beeping their horn. Sounds like you're in the middle of traffic. Okay, so can you see the YouTube?
Yeah.
There. Okay, I'm gonna play it here, and I'm gonna have to do a little bit something funny here so that you can hear the audio.
3, 2 at once in the anti-clockwise direction in a single orbit. 3. Moon rotating once in the clockwise direction in a single orbit. Rotating once around the Earth. Now we can see the moon rotating thrice in a single orbit. Here we can see the moon rotating twice in a single orbit. Here moon rotating once in a single orbit. Here we can see the moon rotating once in the clockwise direction in a single orbit. Here we can see a non-rotating moon. When the moon is rotating once in the clockwise direction, the illusion that it is not rotating arises because for every degree it advances in its orbital path, it is also rotating by 1 degree in the clockwise direction. However, if we observe the arrow with respect to the Earth, it moves away in the clockwise direction as the moon begins to orbit, and at the end of the orbit, it is again facing the Earth. The non-rotating moon appears to rotate in the last video because in it, the Earth appears to have a top and bottom as well as 2 sides. However, in reality, the Earth has no top and bottom or sides. It behaves like a flat surface because, as illustrated in the figure below, although people are standing in different directions, every one of them will feel that they are standing upright on top and the sky is above them. In fact, from every single point on the Earth's surface, we will get the same feeling. This proves that, unlike the current theory, the moon orbits the Earth without rotating by even a single degree. Its motion is exactly similar to that of an aircraft or the International Space Station, which move with their underbellies always pointing towards the Earth. If we travel in an aircraft starting from a particular point, say Bengaluru, and flying continuously until we come back to the starting point, we would always feel that we are flying above a flat or a slightly curved surface, as illustrated in the animation below. At no time during the flight will we feel that we are flying vertically downwards, upside down, or vertically upwards, as this animation implies. Hence, whenever we think of motion around our Earth, we should visualize Earth as a flat surface and not as a sphere. The moon's far side is heavily cratered, whereas the surface facing the Earth is smooth. These are the 2 reasons behind this. 1.
All right, so was everyone able to view and hear the video there? I think that's the relevant parts. So what do people think of that, about this idea that the moon doesn't rotate?
I did not see anything. I just heard some sounds.
You just heard some sounds.
Yeah.
How about Bob? Did you see it? Or Habib, did you see the video? How about Ian? Ian, were you able to see that video when I was playing it?
I was, Franklin, and I had seen it before. And my initial reaction was that I accept that the situation is exactly the same as, say, an aeroplane or Sputnik, an orbiter around the Earth. That is exactly the same. But effectively, that object which is moving around the Earth and has the same face to the Earth all the time is actually rotating once. I mean, you could consider relative to the stationary Earth, if you like, it has actually rotated once. So in a way, it's a bit of a definition. I agree with you that the moon is exactly in the same situation as that orbiter around the Earth. But I would say, well, effectively, relative to the Earth, it is actually rotating once.
When we see the video just before that, where they have shown the moon rotating once, so what do we consider that as? 4, 3, 2, and 1. So that one rotation, it is rotating in the anti-clockwise direction. Either that should be correct, or what you are saying should be correct. Which one of them is correct? Because there we can physically see the moon rotating once. For every degree it advances in its orbital path, it rotates 1 degree in the anti-clockwise direction. We can physically see it, no? So either that has to be correct or this has to be correct.
Well, I think I think we can agree that the last situation is correct, because the other it seems to be an additional rotation. But to say that the last situation which you've given, which seems to be correct, and you're saying this is a counter to the accepted view, is a non-rotating system, I think I would counter that, because there's effectively one rotation relative to the fixed Earth. So it's a bit of a question of definition, but I don't disagree with your animation. I think your animation is correct.
No, because there exactly we can see it rotating once. Every degree it advances its an orbital path, it is rotating by 1 degree in the anti-clockwise direction. And I have shown a animation where the moon appears to be stationary, but in fact it is rotating once in the clockwise direction.
Let me see if I can bring up that video again.
Yeah. That one rotation you please bring up, sir.
I think there's also an issue of definition of rotation versus spin. For rotation,
Yeah, next one.
plotting an orbit, which is defining a plane, which will have an axis perpendicular to that plane. Attach a string to that axis and the object, and that string will wind around that axis and coil up on that. So it is orbiting around. There is a rotation around that axis. In that animation, there's both an orbital and a spin to the moon. And you have to account for both.
Now this is a counterclockwise rotation. So why did you not show it as a clockwise rotation?
No, this is a counterclockwise. The next one is non-rotating according to me, and there's one which shows all the arrows always pointing downwards. That appears that it is not rotating, but in fact it is rotating once in the clockwise direction.
See, I don't get that, because I'm looking at your diagram here, and it has a distinct arrow. Say it's pointing down right now.
No, that's what it is always. See,
so
when it is right on top,
this is going in the counterclockwise direction.
Yeah, exactly. It is rotating.
So why counterclockwise?
I mean it's spinning. You have to account for both. What is spin and what is the orbital rotation?
No, rotation is nothing but an object rotating on its center of axis. See, it is rotating. Here it has completed 90 degrees. Here it will complete 180 degrees. Now here it completes 270 degrees. And now it's completing 360 degrees. This is one rotation, which you can physically see and observe.
One rotation in
the counterclockwise direction.
And a spin around its own axis. Because that arrow was pointing down, then it's pointing to the side, then it's pointing. So it's also spinning.
No, that is the rotation and spin is the same, no, sir. Revolution is different. Rotation and spin is one and the same thing. And can you just show that without orbiting, the moon rotates once at the beginning?
See, I might have said that it's effectively rotating once around the Earth in its orbit, but there is no additional spin. That's the way I would express it. There is no spin, but when you say there's no rotation, I have a problem with that.
I don't know how to clarify, because Mr. Franklin, can you show that a rotating moon, when it is not orbiting, when it doesn't orbit, the first animation.
Very first animation.
Yeah, the first one, where the moon only rotates. It is not. Yeah.
Starting from here?
Non-rotating moon rotates.
Okay, we'll
The first
start
one.
the video here.
This is one rotation. At least, is this correct? At least.
Okay, so rotation and spin are the same. Then I would
Yeah.
say that you want rotation and orbit.
It is the
Two
same.
different
That
things.
should be either in a straight line or a circular line. It should rotate once on an axis. That means this arrow should move away in the counterclockwise direction, and after the end of the revolution orbit, it should come back again to the same spot.
Right.
So you would call this rotation, right? So if the
Yeah, this
moon
is
did
one
this, you would say that the moon is rotating.
Yeah, it once it rotated now. In
But
the
this is what you're
counterclockwise.
saying the moon does not do. The moon does not do this.
Yeah, if it is rotating, we will be able to see all the sides of the moon. Right now, we are able to see only one side. So that will happen when the moon does not rotate.
Well, does the rotating defined by this arrow,
Yeah,
making this path
yeah.
around here, is
Correct.
that what you
Yeah,
define as rotation?
yeah. That is rotation, no?
In this particular picture, I mean, we could pretend that we're looking at the top of the moon's orbit, and this is exactly what we're looking at, looking down,
Yeah,
right?
yeah,
So if I put a big arrow on the moon, then you're defining the rotation as this arrow
yeah.
moving around.
Yeah, that is, the moon is not orbiting, it is stationary, and we are just observing what one rotation looks like.
Well, I'm observing that what's going on with the arrow
Yes,
is what defines whether it's rotating or not.
no, why I have given the arrow? See, before it starts rotating, it is facing the earth. So it is uh, like a central point. So after it completes one rotation, it should come back to the same place. That means the arrow should face the earth again after one rotation.
I mean, if you define rotation that way, of course you're correct. There's no argument. But it appears that what you're saying is for any tidally locked object, or for any object which is circumnavigating the Earth, like say an aeroplane, if it could do that, or an orbiter, you're saying there's no rotation. Whereas I think if you use the word that was used previously, spin, that probably would be more correct. You're saying it's not spinning in addition to its rotation; it's actually rotating once. But we're
Yeah, it is
defining rotation in a
one.
slightly different sense to the way you are.
No, sir. What I am trying to tell. See now in the animation, the Earth appears round and all that, but in reality, it is not so because anywhere we are standing, you see, right now, you people, I am standing in the opposite side in your direction, and you are standing the other way around. But even you feel that you are standing up and the sky is above you, and even I am feeling I am up and the sky is above me. How is it possible? And if I go from the North Pole to the equator, I should stand at 90 degrees. But from anywhere on the Earth's surface, we will feel we are standing on top, and the sky is above us.
Well, I see, Pal, do you have a comment? You've raised a flag. Let's see, does Pal have a comment? Are you unmuted? Actually, he doesn't appear to be on the conference at the moment. there you are, pal. But we can't hear you. So I think Pal's going to have to work on his video, or you can put something in the chat if you have a question.
So can I just ask a small question?
Sure.
Sir, what I want to ask you, at least is the 4, 3 and 2 rotations, is that animation correct? The animation showing 4 rotations, 3 rotations and 2 rotations. Is that at least correct?
Well, it has to be correct. You animated it, I would say.
And then if those 3 are correct, then the one rotation should also be correct, no? If those 3 are correct, how can this go wrong?
Well, it just seems to be a difference between, that's why I was asking about clockwise or counterclockwise rotation. Because the video of the non-rotating moon just appears to be a clockwise rotation of the moon. If you were to animate the moon using a right-hand clockwise animation, then you would have the same situation that you showed in the non-rotating case. So that's why I was wondering why right. It seems to be a choice of which way you decided to rotate the moon.
No, see, the first, when you rotate either clockwise or anti-clockwise, you will always see all the surface of the moon. Only when it does not rotate, you will see only one side of the moon. And you can see the video where the moon appears not to rotate. The arrow is always pointing downwards. There, it is looking as if the moon is not rotating at all. But in reality, if you observe, it is rotating once in the clockwise direction. So that is why for every degree it advances in its orbital path, it is rotating by 1 degree in the clockwise direction. So always as it moves, it goes on adjusting. So the arrow will always be pointing downwards.
I mean, I think all the animations are correct, including the single rotation. And I think we can probably all agree that it is exactly the same as your last animation where you have an aeroplane going around the Earth, showing its base always to the Earth. I think we agree with that. It's probably almost impossible to disagree with any of that. So therefore, I think it's merely a question of definition. I mean, do you maintain that the aeroplane going around the Earth is not rotating?
It is not rotating. It is not tidally locked with the Earth, or whatever it is, synchronous. It is not in synchronous rotation with the Earth.
Whereas we agree with the circumstance, but I would say that the aeroplane is effectively rotating once in its orbit. It's really a question of definition, maybe more than anything.
Then if it rotates, sir, if it rotates once, at some point we should feel upside down. We should feel that upside down. If it is rotating,
well, I would say people do not feel that in the absence of gravity that would happen.
If you took a laser, if you take a laser on the outside of the airplane, point it radially outward, it would point to the various stars as it goes around the Earth. It wouldn't point to one star all the time. And therefore, it's rotating if you look at that system externally. And if the airplane was doing that, what I call orbit, really fast, you would feel a centripetal force, but because it's slow, you don't feel it. And that's another indication that something is rotating.
Sir, can you just put a point?
Well, I think one thing that distinguishes rotating from non-rotating objects is the centrifugal force. So if I'm on a merry-go-round, I can tell whether I'm actually spinning or not by whether I can measure an outward flinging force on the merry-go-round, if it's really spinning or not. So that's the definition of spinning, which doesn't doesn't rely on any reference frame. I mean, you could put yourself in a black box and put yourself in the middle of space, and you could tell for a fact whether you are spinning or not.
Yeah, I got your point, but I would like to explain something. Rotation is only concerning that body. Rotation cannot be related to some other, like example, rotation cannot be with respect to the stars it is rotating, and with respect to the earth it is not rotating. It cannot be. Either it rotates or it doesn't rotate. Rotation is an act of that single object. It is not related to something else. The moon rotates or it doesn't rotate, but it has nothing to do with the stars.
But all motion is defined relative to other bodies. You can't have motion without a reference system defined by
Correct.
some other bodies.
See, now in that single rotation, even there we can see all the stars because that is rotating once. You will see all the stars around it. So, which is correct? What we are seeing, actual rotation we are seeing, it is orbit. I mean, it is rotating by 1 degree in the anti-clockwise direction in a single orbit in one figure, in one animation, and in the other animation, it is rotating once in the clockwise direction.
I think the thing about determining rotation is you're not going to be able to determine rotation from a 2-point perspective. You have to have always have to have at least a third point, a triangulation, in order to determine rotation. If you set that triangulation up so that you have 2 points on the surface of the Earth that are part of that triangle, then those points are always moving with the surface of the Earth, and that base turning also. So the triangle is always going to be staying in the same shape. If you set that third point out in space somewhere, then you'll see that there will be a rotation and a change of the shape of the triangle. So it basically, rotation is going to require that you have a third point or an outside perspective, which was kind of just mentioned. That outside perspective could even be the stars or any other, location. But and then the same thing is true of spin. Actually, to determine whether the moon is spinning or not, you have to have an axis going through at least a couple of points on the surface of the moon that you can triangulate to a third point on Earth to see whether those points are progressively getting, relatively farther and closer to you. And so basically, it's really a matter of perspective of where you choose the points as to what you say is rotating and what is spinning. And as far as, determining whether or not you're rotating based on the force, you still need a mechanism to measure the force even. And that mechanism to measure the force usually involves an instrument with a certain length of distance that can be, measured the force, and that instrument can be measured between 2 points. So even there, you're pointing your instrument at the moon or whatever, and so then the two ends of the instrument are pointed at the moon. You're measuring the distance between those two ends to see if it changes, like a spring stretches or not, to see if there's tension. And that gives you the perspective of 3 points, basically, that you always need at least 3 points to determine rotation or spin. That's my take on it.
So, okay, finally, what shall we decide that single rotation, whether it is rotating or non-rotating? That one rotation, what I have shown in the animation, what shall we call it? Is it rotating or is it not rotating?
I got to ask, was anybody hearing what I just said, or did my mic go? Is my mic dead?
Now, we heard you.
Okay, thank you.
Yes.
So, what do people think?
I think, I don't want to be too dismissive, but I think it's a bit arbitrary what definitions we use. I think we're sort of in agreement on the outcome, and whether we call it non-rotating or rotating or spinning or non-spinning, it's a bit arbitrary. But I'd like to ask, because you said earlier, I think, that it was not tidally locked or not gravitationally locked. Now, there seems to be a tendency for orbiting bodies to become so locked, in conventional speaking, we call it tidally locked, that seems to be a normal situation to which they revert ultimately. Do you not think there's a physical reason for that, from the gravitational theory?
I don't feel so. Because actually we are seeing it rotating. No, it is not something we are imagining. We can see it rotating 4, 3, 2, and once. So only one can be right. One, what I am showing is correct, or the other one should be correct. In the other one, we cannot. The arrow is always pointing towards the earth.
Yeah, I understand that, and I think we agree what we see. But I'm asking, why don't we see it rotating 3 times or 4 times, or once the opposite direction? Why do we see this system, whatever we wish to call it, such that we only see one side of the moon? And that is not a singular circumstance. It does occur with, the closer planets as well. It seems to be a sort of a system that gravitationally orbiting planets revert to. It's a stable system, a reasonably stable system, tidal locking. But you seem to be dismissing it. Is it just a coincidence?
No, no, sir, it is not a coincidence. What I am trying to say is, what that means what we are seeing is wrong. That one rotation is wrong. Moon is not rotating that time. But it is physically we can see it moving. See, it should be very clear. When it orbits, we should be able to tell in a single orbit as it advances in its orbital path by how many degrees is it rotating. For every degree it advances in its orbital path, how many degrees it is rotating on its axis. That will be a more scientific way of putting it. Because exactly that is what is happening. As the moon starts to orbit, it starts to rotate by how many degrees for each degree of orbit advancement. Don't you think it will be more scientific that way?
I think, I mean, part of what you're talking about too, Ian, and what we're saying here is that, why does it rotate in synchronous to the spin, rotate in synchronous to the Earth's rotation? And I think what I've heard is some explanations of that before was that the origin of the moon was basically a separation of a part of the Earth when the Earth was more of a liquid form earlier. And so just like a piece of the surface of the Earth is not rotating with respect to the rest of the Earth, if it was just something that broke off from the Earth, then they would have no point in acquiring spin, whereas if it was a separate satellite that was captured within the gravitational pull of the Earth, it might have a spin of its own. So I have a tendency to believe that its origin was probably that it was originally a part of the Earth system, and just either broke away or part of the entire Earth system of components that came together to form the Earth, and it particularly didn't come together. But the reason it doesn't have a rotation is kind of just a question that's been thrown out there before.
So I'm just, you guys seen the animation, right? I'm just reviewing the difference between the one rotation, since the point is like if the moon rotated once, this is what it would look like. Okay, so the assertion is if the moon rotated once during its orbit, like mainstream says, it would do that. And it's showing all sides of the moon towards the Earth.
Correct.
Right? So people get that, right? So let's jump to the video of the no rotation video here and see what the difference is. Okay, so let's see here. So that's finishing up that. Okay. Okay, so this is the no rotation video. So in the previous video, we saw that if it was rotating counterclockwise, it showed all its faces to the Earth. So let's see what it does here. So it still appears to be rotating in the counterclockwise direction. We've started the arrow pointing down. And now it continues to do its apparent rotation, but yet is only showing the same side to the Earth. So it looks like it did exactly the same thing as the previous video, but it maintained its face to the Earth. Now that's rather confusing. At first glance, I cannot figure out how that happened.
Confusing. The problem is you're changing your perspective. If you use the perspective of 2 points on the Earth to reference your rotation to in both cases, in the second case it didn't rotate at all because it's always equidistant from the 2 points on the Earth's surface. If you take your point and put it out in space, you've changed things entirely. So if you look at the 3 points, one being the Earth and another being a star out in space, and you look at the
No, I don't think
video,
it has anything to do. I think you missed my point. Is that I'm confused because in both cases the moon rotates counterclockwise, and in one case the moon shows its face, its entire face to the Earth, and the other case it only shows like the part that the arrow's pointing to. So that doesn't have anything to do with the reference frame. I'm just saying physically what part of the moon is being shown to the Earth. In both cases, the moon is rotating counterclockwise, but there's a radical difference in the surface shown to the Earth.
In the first case, it's rotating twice. In the second case, it's only rotating once.
No, actually, I don't think it is. I think it is still only showing one rotation.
Look at the first case again and put 2 points on the out in space, not even relative to the Earth, and just set 2 points out in space and measure the relative rotation to them. Then do the same with the second one. You'll notice that in the first one there's two rotations, and in the second one there's for one rotation. Just ignoring the location of the Earth, just set 2 points arbitrarily out in space away from the Earth, and then measure the rotation with respect to those 2 points. The confusion is that you're using a rotating reference point on the surface of the Earth in one case and not in the other. So it's an illusionary creation because you're changing points of reference.
I don't think so. Okay, so this is the video showing a single counterclockwise rotation around the Earth.
Okay, ignore the Earth. Just put 2 points out on the right-hand side of that diagram.
Even if you do that, that's still a counterclockwise. But you see that what I'm noticing here is that the degree of rotation is a lot higher.
That's right, so because compared to by the time it gets around, it's actually rotated twice.
So let's see here. So if it's only doing, let's check to make sure it's only doing one rotation, because I would predict that this will be doing more than one in this diagram, because there has got to be an explanation. All right. So there, now it's actually back to where it started, right?
No. The direction is opposite. Now we are seeing the opposite side of the moon.
See, this is claiming to do one rotation, but it's just completed
only half a rotation.
Let's start. Let's start again here.
Yeah.
Three, two. Unfortunately, it's a little bit hard to get the diagram back to exactly where.
This is two rotation.
Okay. So this is claimed to be one rotation. So I'm defining rotation as when this arrow gets back to pointing downward.
Yeah.
So when does it do that? It does that. So there, it has completed one rotation already.
No, sir. Half rotation. It has
No, it's
completed.
rotated all the way around. It's gone 360
No.
degrees.
You come back. I will show you.
It has,
360.
it has spun once around its axis
No.
and orbited only a half.
Yeah. You please move it now.
So
See.
that is about 45 degrees of rotation.
No. You
That
bring it here.
is 90 degrees rotation.
Yeah. No, not there, sir. That is not 90. 90 is here.
See,
When it
90,
comes.
see, we started here. Look at the arrow. The arrow is
No,
pointing directly
no,
right.
yeah. No.
Yes, it's pointing directly right. Right? You would agree. This arrow is pointing 90 degrees to where it was before we started.
No. When it comes here, it is 90 degrees when at this point.
So that's where it starts. So what degree is the arrow pointing in this picture?
This is the starting point, and it will
what
rotate
degree? What degree is that arrow pointing?
zero.
The only
You can
acceptable,
see
okay, 0.
zero.
This is what you define as 0.
Okay.
Okay, now what angle is the arrow pointing at?
No, with this it is 90.
No, this is, yeah, this is at 90 degrees.
No. See, but actually from the reference point, it has rotated only 22.5 degrees. It should be from this point. See, now it started from here, right? The arrow was facing the earth. So from this point it will come now. From this point, see. Okay.
So I'm looking at this from the top. So the
Yeah,
only degrees of angle.
Please, you slowly move it. I'll show you what is happening. Yeah, please move it slowly.
Well, that's 0.
Now come along with this. No.
That is 90.
This is the point. That is showing 90, but this is the point from where we have to take the measurement. See, this is the point. This is the point from where we have to...
Well, I can't see your. I can put it. I think I need to give you a little bit of control so you can. Let's see here. Let's see if I can give you the arrow because I cannot see what you're pointing at.
Okay.
So let me see if I can promote you. Now, there's you may be able to see that on the left-hand side. There's a little like laser pointer or something. I don't know whether you will or not, but you may be able to start pointing at stuff if I share something. Let's see if that works. I don't know if it will or not. I think if you're pointing at something, we need to know what you're pointing at. Or I can point for you. I mean, where do you want to point? Can you see my pointer?
Yeah. You bring it still this side.
So where do you want to put your pointer?
No, I cannot show because you're not able to see my thing, no?
No, I'm not able to see anything. So you're going to have to tell me where to put the pointer that I can move around. You can tell me to put it anywhere you want.
No.
Where should I be pointing at?
No. It starts from here. The reference, it has turned only by 22.5 degrees, not by 45 degrees.
No, I can see that the moon has moved 22 degrees, but in terms of its rotation, which is defined by this red line, it has gone 90.
See, that is because the angle has changed. As it changed, it is how do I explain it? Okay, sir, then if one rotation is completed here, then we should see the same side, no? You please bring it 180 degrees.
So that's 180 degrees.
No. One rotation is here, and at one rotation we are seeing the far side of the moon. If one rotation, the arrow should again point towards the earth. Only then one rotation is completed.
Well, that's because this thing is not doing one rotation, it's doing two.
Then when you do two rotations, how much is that then? When I shoot two rotations,
I mean, do you get my point that this animation is showing two rotations of the moon?
no. You see the first thing, only then you will understand. The first animation, a non-orbiting moon rotating once. You just
Yes,
see
and it
that.
showed. Let's go back to that.
Yeah, and you place it along with this.
Okay, this is your example of a non-rotating moon, and in this
A non-orbiting moon rotating once.
non-orbiting
Rotating
moon,
once.
rotating once, and when we run this, you'll see that this arrow goes around once and ends up in its down pointing position.
Yeah, then only it
once.
is completed one rotation. That is one rotation.
Now, in the other video where you show supposedly one rotation, we'll see the moon move around, the arrows moves around, and when at the bottom, it looks exactly like this.
No, you see that the arrow is pointing downwards. You are not seeing this portion of the moon. You will be seeing this portion of the moon. You can check up.
Well, yes, you will see that.
Opposite side of the moon. If it has completed one rotation at 180 degrees orbit, then we should be able to see the back portion of the front, the arrow mark again.
No, my argument would be that you don't. You wouldn't expect it because the other diagram is showing the moon rotating twice, not once. I mean, do you understand the?
See, rotation.
What you call one rotation, we normally would appear to be calling twice. And what you call twice, we call three times. And what you call three times, we call four times. And what you call zero times, we call once. So it appears that you're subtracting one of the rotations, probably owing to the orbit. So it seems to be just a way of looking at things.
Well, let's look at this animation again. So all that happens is that the arrow rotates once.
It comes back to the starting point.
Yes, it comes back to the starting point.
Yes, that is one rotation. That same thing should occur in one rotation while it is orbiting.
Now, in your diagram of one rotation, we see that it rotates around, and then the arrow pointing down, it rotates around till it gets to this point, and it's pointing down.
Yeah,
which means it has completed. What does that mean?
Half rotation. If it has completed full rotation, if it has completed full rotation, the arrow should again be pointing towards the earth.
Why would that be?
Yeah, that is one rotation. See, one rotation always, whether here or whichever position, the arrow should move away and come back to the starting point. That is one rotation.
Well, I think maybe this is the difficulty here, because if we were to just ignore that this is the planet Earth, and we were to just put a protractor on this screen with 0 to 360, then we would say that with the moon, even if it's over on this side of the planet, we would say that the arrow is pointing at 0 degrees, and that no matter what this is, that if this thing is rotating, and by the time it reached this point, it was at 0 degrees, what would we conclude? That it rotated half, or that it rotated once?
It rotated half.
So how many people agree with that? That after the moon does this entire motion, 360 degrees, such that it's pointing to 0 degrees, that is half a rotation of the moon.
No. In the instance where the arrow is pointing down, not towards the earth, then it is half. If it is pointing towards the earth, then it is one full rotation.
So how does it make any difference whether it's pointing towards the earth or not? I mean, the earth and this situation doesn't matter. Let's blow up the earth so it doesn't exist.
You do that. You remove it. You remove the earth and do it.
Let's remove the earth. So okay. This is spaceship moon, and we're just powering it around its orbit. And so I'm doing this, and it's spinning around, and then at the end, and we just have another spaceship which is just looking at the top. That would you say that as soon as the spaceship finishes spinning and it's pointing once again in the 0 degree direction, that the spaceship did half a rotation?
If it is facing the earth, it is.
But there is no earth. We've gotten rid of the earth.
Okay. If it is facing, if the arrow is pointing upwards, then it has completed one rotation. But if it points downwards, it means it has completed only half a rotation.
How can it have only completed half a rotation? I mean, basically what you have said defies the laws of geometry.
May I have a turn?
Please.
It sounds like that we're trying to put two different labels on the same fact. We all agree with the correct diagram where the arrow always points to the earth. Any diagram where the arrow does not point to the earth is incorrect. Therefore, whether we call it 1 rotation or 50 rotations makes no never mind. All that matters is that we all understand and believe that as the moon goes around one time, the arrow always points to the earth. Does anybody disagree with that? That the arrow always points to the earth in reality. That's the reality of the situation, regardless of what we term it.
I think everyone would agree with that, but does that constitute 1 rotation or no rotation is the crux of the problem here?
I would call it 1 rotation. But if somebody wants to call it no rotation, what difference does that make? We all understand what the actual fact of the reality is. Why are we messing around with the semantics of whether to call that a rotation or not a rotation? What are we trying to accomplish?
Well, I think from a scientific experiment perspective, if you put a sensitive instrument on the moon and all it would have to do is measure the weight of an object, that if you spin up the moon, that you will see that objects on the moon would appear to get lighter as they are flung out. Or, people say that if the Earth is actually rotating, that its equatorial regions, being more sensitive to centrifugal force, actually bulges out. So there is a physical consequence of whether the moon is spinning or not. A spinning moon should have this equatorial bulge. You should be able to put instruments on the moon that can actually detect this. Or, we see like the Foucault pendulum, which can detect the rotation of the Earth, that it moves because there is a true rotation of the Earth. So there is an absolute quality to whether we say the moon rotates or not.
The center of mass of the moon is inside of the Earth. It rotates around a point that is inside of the Earth.
And your point is?
That if we want to discuss whether that equals considering it rotating or not is besides the point. Why don't we just use the diagram and all agree that when we see the diagram is correct, we go, yes, we all agree that's the correct diagram, and then continue the conversation instead of trying to label it. Just use the visual representation as an agreed upon fact.
So what would be the continuation of the conversation? Because I think the whole conversation is supposed to be centered around whether the moon is rotating or not. And the whole point here is that it depends on whether you take 2 points on the Earth as your reference point on your triangulation, or you take 2 points out in space to determine whether or not whether it's rotating or not. It's a matter of perspective where your points are that you're using to measure the rotation of the moon against. If you're always against on the Earth, it's not going to be rotating with respect to the surface of the Earth because they're both rotating in synchronous. Your reference line is rotating synchronously to the moon, as opposed to if you put it out in space, your reference line is steady state and you are then seeing the rotation of the moon. It's all a matter of perspective. Where this conversation is going to go once we establish that, I don't know, but that's...
Well, that's why I was asking about the gravitational locking. I mean, we're all agreed on the circumstance. I mean, that's empirical. That's what we observe. And the previous speaker, but one, is possibly right. I mean, it doesn't matter whether we call it 0 or 1 or 500 revolutions, or we agree with this. But looking at it physically, the reason the moon is presenting the same face to the Earth in its orbit, well, conventionally, that is because of tidal locking. As was said earlier, the moon probably came from the Earth, and in its normal orbit, there would be a tendency for it to spin rather faster than it actually does. But the Earth's gravitational field is locking it in and making it spin more slowly, such that in conventional speak, we talk about it rotating once in its orbit. And in this new speak, if you like, we'll call it 0. I'm not going to argue about that. But I'm looking at the physical reasons behind the circumstance.
Well, I don't know what tidal locking means, but if you think of like a sailing ship, I saw an example of this yesterday, that they put all the rocks down in the bottom of the ship, and that's what keeps the ship upright. Because if they didn't put that there, then it would just lean over and sink. So, as far as an explanation for that goes, I don't think it has anything to do with tides. I think it just happens to be that any given object like the moon is not uniformly distributed, and one side of it has got more mass than the other. And if you think of it like that, then it's just staying upright like a ship that's been ballasted with all these rocks in the bottom. And so it will obviously sail with all the rocks pointing towards the Earth all the time. So how's that for an explanation?
I get Ian. On the question of why it is or isn't spinning, you're saying that if it came from the Earth, when it originally came from the Earth, it would come from the Earth's surface that was locked to the Earth and wouldn't be spinning. Why would we expect to obtain a spin? I guess the question.
Yeah, so I just presented a hypothesis with this. It's just like a sailing ship. And of course, it's going to present its belly, heaviest part, towards the Earth all the time.
Well, assuming we can't really tell whether there's the heaviest part or not, but assuming if it were not, if the mass was evenly distributed, is there any other reason that an evenly distributed mass would start to spin? That's the question I'm asking.
No, I don't think it would. I mean, I think logically we would think that if it was totally evenly distributed, there's no reason why it would be pointing at the Earth all the time.
This is not a normal situation. I mean, there is a tendency to revert to this, as I said earlier. But I mean, if you look at all the planets and their moons and so on, you'll find a complete mishmash of orbital periods, of rotation periods, and even directions on occasion. So it's not the norm where you have a circumstance like this, although it is a stable situation. This is why I go to this gravitational locking, because it's one explanation for a sort of a stability and why this would be a result. But it's not necessarily. I mean, take the Earth itself in its orbit around the Sun. Well, it's spinning much faster than it's revolving. It spins 365 and a bit days, 365 and a bit times. So, there's a situation where we don't have a one-to-one correspondence.
Yeah, but in the case of the Earth being captured by the moon or by the sun, we're thinking more or less in the event of the creation of the solar system that theoretically the Earth was captured by the gravitational pull of the sun. It was pulled towards the sun, as opposed to our moon, which we believe maybe have come from part of the Earth. And in the case of some of the other planets, we're looking at the debris around Saturn and that, and we're looking at the moons and that. Now, the question is, do we believe likewise that all that debris and or some of the moons came from those planets, or were they collected by the gravitational pull of the planets? And maybe that's the distinction as to whether we have this spin or not, is how these planets and moons came together. Whether they came together or they came apart might be the distinction as to whether we have the spin or not. That's just an estimate or a possibility.
So I'm just going to go back to the so someone made a claim that the number of rotations being counted out is lacking by 1. So I don't know. Let's take a look at that. So let's say 3. Okay, so I'm going to count every single time I see a rotation. That's once. That's twice. That's 3. That's 4. So who agrees with me or disagrees with me that was 4 rotations and not 3?
Agreed.
Yes, I agree.
So you agree that is, well, Habib, what do you think? Was that 4 rotations or 3?
Depends on whether you look at the perspective of the Earth rotating once during that time too. And that's it. Did the Earth rotate? And in this diagram, the Earth didn't rotate at all, right?
In reality, it rotated 27 times.
No, I don't think it did that. If that was meant as a joke, it's not funny.
When the moon goes around the Earth one time, the Earth rotates 27 days.
Correct.
Well, that's true.
With respect to the sun.
Yeah, it's 29 and a quarter, actually, I suppose, with respect to the Earth itself. So, you have to be careful here. But certainly, relative to the fixed stars, if you like, I think we're lacking by 1 in the description of the net number of rotations.
Yes. Habib, what do you think? Is it? Did you miscount or?
No. There's no miscount. I'm very, very correct. What I would suggest, see, we have to go scientifically here. The moon is orbiting. For every degree it advances in its orbital path, if it has to rotate by once, then it has to complete a full orbit. Now, if it has to complete 2 rotations in a single orbit, then 360 divided by 2 is 180 degrees. So it will complete one at 180 degrees and complete the second at 360 degrees. Now, if it has to complete 3 orbits, divide by 3, it comes 360, 120 degrees. At every 120 degrees, it will complete an orbit. And if it has to rotate 4 times in a single orbit, it has to complete an orbit in every 90 degrees. This is a simple calculation. 4 divided by 360, 90. So every 90 degrees, it has to complete an orbit. There is no argument about this at all. You have to go scientifically. You just divide the number of degrees by the number of orbits required. Finished. 2 orbits, 360 divided by 2. 3 orbits, 360 divided by 3. That is the equation.
Was it me, or I did not understand a word of what was being said there? I mean, I don't mean to be facetious, but it's like, in order to, the proper calculations is that for 3 orbits, that should be times 360, that should be 1,080 degrees worth of rotation, right?
No.
So in this diagram here, I should see 1,080 degrees worth of rotation. But I in fact see 1,440 degrees worth of rotation in this diagram. So it's not agreeing with the facts of geometry. Now, can someone else help me out here? Because as moderator, I'm really not supposed to be this opinionated.
I just think it just misstated the use of orbits. It just meant rotations of the moon, I believe.
I don't think it's a misstating. I mean, it's just not right. I mean, under no circumstances can this particular animation be said to be only having 3 rotations.
Don't go by animation, sir. Let us just calculate, like I said. Calculate, see, one revolution is equal to 360 degrees. In one revolution, if the moon has to rotate once, then by how many it has to make one full round? It will rotate by 360 degrees. I think that is correct.
See, I'm not prepared even to counter that. I mean, I'm willing to accept that. If you take it that this hypothetical aeroplane going around the Earth and showing its underbelly to the Earth the whole time is not rotating, okay, fine, I'm not going to argue with you. Let's take that as a definition. And if that's a definition, I call that rotating once. If you call that, if that's your definition, well, then you have to subtract 1 rotation from every other description. And let's do that. Let's accept it. But I'm asking physically, if you say that the moon is actually not spinning at all, I mean, the normal circumstances is that you will have some spin of any orbiting body. If it's completely stationary, if there's 0 spin, what is the physical reason for that? That would seem very strange, wouldn't it?
The reason I'm not too sure about that.
My opinion is that the Earth gave birth.
Can I give another example, sir? One last example I will try. I might be wrong, I don't know. You just, in that position, imagine a rod is connecting the Earth and the moon. A rod is physically connecting the Earth and the moon, such that the moon will not rotate at all. We have tied a rod, just an imaginary thing. We have tied a rod to the Earth and the moon and we have joined them together. Now let the Earth rotate and you see what happens. The moon cannot rotate at all then. It is fixed to the Earth with the rod.
But it is still rotating with respect to space.
No. How can it? It is fixed to the Earth. How can it rotate?
Because it has to rotate because it is fixed to the Earth. The Earth is rotating.
Exactly, sir.
Therefore, everything attached to the Earth must be rotating as well.
No. Rotation means when an object rotates on its center of axis. But when it is fixed to the Earth, how can it rotate? You just tell me.
Because it's fixed to the Earth. It's part of the rotating Earth. Right? It's part of the rotating Earth. Therefore, if the Earth rotates, then everything has to rotate.
No, sir. What I'm telling you, imagine we have taken a rod. It is just imaginary. We have joined the Earth and the moon with a rod. We have fixed it. Now, can the moon rotate? You just tell me. It is fixed to the Earth. How it can
Yes.
rotate? It is fixed to the Earth.
Well, relative
How
to
can it?
what?
How can it?
I mean,
How can it not rotate? That's my
relative to
question.
the
How can
sun,
it
it's
not rotate?
rotating.
How can we fix the
Okay,
moon to
let us
the Earth
forget the
when
moon
the
and
Earth
Earth.
is rotating 27 to 29 times per moon orbit?
No.
It would
Let
need
me
to
give
be
you
like
another
a
example.
string around like a yo-yo string around a central core, so that the yo-yo can still turn while the moon is still connected by that string.
Let's make it worse. Let's put the moon directly onto the Earth, just like it's standing on the Earth. Now, when the Earth rotates, then it's dragging the moon along the surface, and it is, yes, it is in fact rotating. If we're looking at it from the top axes of the rotating Earth, we see the Earth rotate, and as we see the Earth rotate, it's dragging the moon. And if rotation is determined by a spin of a fixed point on the moon, we would see that when it reaches the bottom here, that it is in fact pointing the opposite direction, that it has gone 180 degrees, and then when it comes all the way back up here, it comes back to its original starting point, which is 0 degrees, and by that definition, we define that as a spin. And definitely, if the moon was sitting on the Earth, it would feel a centrifugal force due to its spinning action. So all of those things prove that it is really spinning.
No, I will give another example, sir. Now, this is, last try for me. Now, we have got two steel balls in our hands, see. One representing the Earth, the other representing the moon. If I put it on the table and spin, it will rotate individually. Both the balls will rotate individually. That is called rotation. Now, if I take a rod and weld this ball to the other ball, both the balls with a rod, how can the ball rotate? Both the balls will not be able to rotate. It will not be able to spin on its center of axis.
But it would still be, if rotation is just
something like
the
this. I will just
definition
make
of,
a diagram.
I mean, they don't have to spin. That doesn't matter whether they're locked or not.
No. Right? It is important. Why?
It's not important. That's not the definition of spinning.
Yeah. See this. I will show you. If you can see this, can you see this?
Okay, let's see. We've got to.
Okay. Now we have got individual two balls. You can spin them. In the first case, there are two balls which can be spun independently. Now I have attached a rod to both. When we spin them individually.
See, now you're showing this on your video, but for some reason your video is frozen to me.
Oh, sorry.
Is anyone else seeing that?
No, it is not a video. Sorry, it's not a video. It's just a sketch I've made.
Yes, I'm getting it.
Let's see.
I'm seeing it.
Just not frozen to me, frankly.
Yes, I see it as well.
It's a little low.
Another example might be
now you can see anything.
A sling with a stone connected to a central handle, which you're slinging around. And the stone cannot have any additional spin other than that permitted by its revolution around.
These two individual balls are, one is the sun, one is the earth, and the other is the moon. In one case they are free, in the other case they are joined together. How will they spin? On their center of axis.
No, not all spins are dependent on central axis.
Yeah.
Rotation. We have to talk about relative to what? I mean, the moon is not spinning relative to the Earth if they're joined together, but relative to the sun, they're both spinning.
No, sir. Once it is fixed, how can it spin? I'm showing here, no?
I mean, if I take this thing and I rotate it around like this, it's not spinning around its center of axis, but it is still definitely spinning, right? It doesn't matter. If I do this, it's not spinning around its center of axis, but it's still spinning, right? It doesn't matter that it's not doing this. This is not the only case of spinning. This is also a case of spinning, right? Doesn't matter.
we can't see what you're we can't see what you're presenting because we see the white sheet of paper. And we're not seeing what you're showing.
You can't see my video? That's all I'm doing. I'm just spinning a candy bar in around my head in space, showing that it doesn't matter that that's not spinning around the center of axis. It doesn't matter. I can spin that candy bar around my head. It just that's not
correct.
just,
You can do that, but that is not
What
rotation.
I see right now is a presenter.
The definition. Excuse me. The definition of rotation is the act of turning on its center of axis. Anything else is revolution. The definition of rotation.
That may be where we disagree.
It's the act of turning on its center of axis, not on somebody surrounding somebody. That is the meaning. I mean, definition of rotation.
Well, I guess we'll have a disagreement with that.
Okay, sir.
Rotation should be defined purely as its vector direction, and if that vector direction changes, that is rotation. It doesn't have anything to do with the center of axis.
I think the distinction might be just a difference between the word use of the terminology spin and rotation again.
And my bandwidth is getting a little bit low here, so.
It's a bit arbitrary anyway. I mean, according to one definition, all of us on the Earth are rotating once every 24 hours. That's probably the definition I would be using. And according to your definition, sir, we're rotating 0 times every 24 hours.
No, we are rotating 24 times, not 24. In one day, 24 hours, we are rotating once.
Yeah, but that's contradicting what you've said earlier. We're exactly in the same position as the moon. I mean, earlier it was said, suppose the moon is right on the Earth. Well, we're like the moon. We're locked to it. We're showing. Say we're standing on the Earth. We're showing the same pair of feet to the Earth's surface as the Earth moves around once. So, according to your definition, we are not rotating when the Earth moves around, or when we move around once with the Earth. And according to the definition of probably most of us here, we're moving once. I mean, we agree on what is the circumstance. I think that the rest is really semantics. It's probably not worth getting very much het up on.
Sorry, no, I don't think it's semantics at all. I mean, really, I would, really disagree that this is a matter of semantics. That there really is a problem here.
I think I agree with Rian. It's just a matter of semantics and how we use what perspective we utilize. I mean, even he is saying, we rotate once in a 24-hour period. The difference is if I'm standing at the North Pole, I'm actually spinning, right? Because the center of rotation is in the center of me, so then I would call it a spin. So that's, again, perhaps a matter of semantics, but the spin...
Now, as a moderator...
Spin, in my opinion, is probably when the center of rotation goes through, is in rotation to be when the object is not necessarily having the center of rotation in its center. But again, it may be just a definition.
No, I think the reason why I think it's not a matter of semantics is that geometry is a very precise science. So that in this diagram of the moon going around the Earth, we should be able to conclusively agree when we see this, how many times it's going around. It can't be a matter of semantics that some people say it's 1 and some people say it's 2. That can't be a matter of semantics. So when we make this video go forward, so this is once, that is twice. That's not a matter of semantics.
Okay, it's still a matter of how people utilize the words. How people define rotation and how people define spin.
Well, I think there's only one that makes sense, and that that diagram just showed a rotation of the Earth, of the moon twice.
Okay, well then let's look at another situation. Let's look at clockwise versus counterclockwise. Is that a matter of perspective? Is not a matter of actual direction, right? So isn't this somewhat the same thing? Which is it counterclockwise or clockwise when I'm looking at something spin or rotate?
No, I think it is a difference. I mean, definitely there's two rotations going on here. There's no way it can be said to be
But
one.
if I look at something from the back side of a clock, then it's spinning clockwise. If I look at something from the front side of the clock, it's spinning counterclockwise. If I look at the Earth from the North Pole downwards, it's spinning counterclockwise. If I look at the Earth from the South Pole upwards, it's spinning clockwise. It's just a
clockwise is different. Clockwise is different. In this particular diagram, is there any way that you can fathom in any perspective where the moon is only rotating once?
We're talking about two different rotations and spins. If you have two things spinning and rotating, then you have a reference where you can only distinguish clockwise and counterclockwise. If you just have one object rotating or spinning around, then you can't distinguish clockwise or counterclockwise unless you look.
But I'm not talking about counterclockwise and clockwise. I mean, certainly there could be that confusion in that case.
I'm just saying that they're both are a matter of perspective, whether you're looking at it from the outside of the Earth system or from the Earth's surface.
But it's the speaker who thinks that this indicates one revolution. Franklin, with respect, you should ask him to explain why he thinks it's only once. I mean, we're all agreed on what is the actual outcome. That's why I say it's rather semantical, because we agree on the outcome. But you should really ask the speaker as to why he considers this as a single revolution rather than two.
Sir, okay. Please give me a chance. I will explain. Sir, for everything we can decide by calculation, right? By calculating, we can find out. We need not even go into the animation. Now, I will just say one revolution is equal to 360 degrees. So now my question, one small question is there. How many degrees has the moon should advance in its orbital path to spin 10 times in one revolution? How do we calculate it? Moon has to make 10 rotations in one revolution. So how do we calculate it? 360 divided by 10 is equal to 36 degrees. Every 36 degrees, it advances in an orbital path.
No. How many times it has to rotate is 10 times 360. Yeah. 10 times, not divided. It's 10 times. Has to go through 3,600 degrees of rotation.
No, not the moon's rotation. I'm telling in the orbital path. See, in one orbital path, it is covering 360 degrees only. In that, I'm telling, not the thing, how much surface area the moon covers, that is not important. See, once the moon completes the orbit around the Earth, it completes 360 degrees. In that 360 degrees, it has to make 10 rotations. So how do you calculate it?
Calculate it in terms of...
No, nothing. One revolution is equal to 360 degrees. All I'm saying is 10 times the moon has to rotate in that 360 degrees. So how many degrees, how will we calculate? It is very simple. Divide 360 by 10. You will get 36 degrees.
Okay, so at 36 degrees, it should have completed one full rotation.
Yes, correct. For every 36 degrees, if it completes one rotation, then when it comes to the final thing, with 360 degrees, it would have completed 10 rotations. By going with the same logic,
not divide.
It's okay. Please don't interrupt. I've got it so far.
Yeah.
So continue.
Yeah. So 10 times. Now I want to rotate it 5 times in one orbit. So then it becomes 360 divided by 5. 5, 6, 30, 5, 6, 66 degrees.
That would be 72 degrees, right?
Yeah, every 66 degrees, it has to complete one orbit. This is the calculation. Okay, now I will say one revolution it has to complete. Then 360 divided by 1 is equal to 360 degrees. That's all. And 2 revolutions, 360 divided by 2 is equal to 180 degrees. So at every 180 degrees, it has to complete one rotation. Simple maths.
Well, if it was to complete 360,
Yeah.
300, it would complete 2 rotations, then every divided by 2.
180 degrees.
Then at 180 degrees, it will have completed 1 rotation.
Exactly.
And
Yep,
then
perfect.
when it does the other half, it will have completed 2 rotations.
Yes, when it comes back to the starting point.
This is what your diagram currently shows.
No,
that
no.
at 180 degrees, it's 1 rotation.
No, it is rotating only half. You can see the arrows pointing down.
By that same thing, it's like if we have to rotate, if we do 2 rotations, then by the time it reaches 180 degrees, we'll have already done the 1.
1, yeah, exactly.
So therefore, this diagram cannot be showing only 1 rotation because it's not even back to where it started.
Okay, then you please show me 1 rotation. How will it complete 1 rotation?
Okay, this is 1 rotation. It's pointing down. Well, this is not that one. This is we need to go to your 1 rotation example here. Okay, here we go. This is the 1 rotation ever does this.
If you go to the 0 rotation, you'll find what you are claiming to be 1 rotation.
Yes, so I mean, we take in order for this to be 1 rotation, it would take just one of these things before it got back to pointing downward. But I claim that this is showing 2 rotations, that by the time it reaches the 180 degree mark, we predict that it should have gone through a full rotation in order for it to be 2 rotations. So looking at this, there is your 1 rotation. At 100, by the time it reaches 180 degrees, it has done 1 rotation. So any further movement of the moon means it's doing more than 1 rotation. In fact, it goes on to do the 2nd rotation. So this, by your math, is 2 rotations. Do you agree or disagree?
I don't agree, sir, because 1 rotation means 360 divided by 1. It will complete 1 rotation only when it comes to the starting point.
And right, and it came to its starting point when it was over here.
No, where the arrow is pointing downwards. It has completed only half its rotation.
That's because it spun twice. It's pointing back down because it spun twice.
How? I just know how to think because I'm so confused now.
Well, watch. Let's just watch this. Okay, does it do 1 or 2 rotations? Watch the arrow, because the arrow, I claim, is going to go all the way around 360 degrees,
yeah, you showed
back
it
down, and then it's going to go all the way around and do it again. And that's why we see it back in its starting position. So let's watch carefully. That is a complete rotation.
That is half rotation.
Now that is a complete rotation. Let's take a look at it again. Watch it carefully. A full rotation means that the arrow goes all the way to the right, up, left,
when the arrow comes
down.
Excuse me, a full rotation is when the arrow comes back pointing towards the earth, not away from the earth. It should come back pointing towards the earth.
No.
The earth, only then it completes one full rotation.
No, that would not be correct. Because it doesn't matter that the earth is here at all. It doesn't matter that the earth is here at all. I mean, so far as geometry is concerned, if I put a protractor in here and we eliminate the presence of the moon, which we should because it doesn't really matter for purposes of rotation, that the rotation is just dependent upon whether this arrow ends up going back to where it started. It doesn't matter that the earth is here.
So that is why I said we should not get confused. That is why I showed once the moon orbiting without, moon rotating without orbiting. The first animation. That is why I showed that. That is one rotation.
Yeah, and you showed one rotation, and this moon just did that motion.
How can it's pointing the other way?
It's not pointing. It's pointing in the same direction,
No,
which is towards the
we are
bottom of the
seeing,
screen.
we are seeing the other side of the moon now. From the earth, we'll be seeing the other side or back side of the moon, not the front side. Only when you can see the front side, it has completed one rotation.
I think I'm beginning to see the problem here. But you would agree that if the moon didn't exist at all, that that would be one rotation. I mean, if the Earth didn't exist at all.
No. Even then, it is not one rotation, because if it completes one rotation, we should see the starting point again.
And
But
we do see the starting point from the perspective that we're looking at it.
No, from the Earth, you are seeing the other backside of the moon now.
Now I'm just looking at the top. We're looking from the top, and we're looking at this diagram of the moon that we have here. And we can see like the smooth side is on the right, and the rough side is on the left. And if we go and we rewind this back to where we started, so there's the starting point. We see the smooth side on the right and the rough side on the left. And so that's what we consider return back to the original rotation, because we're looking at it through the rotation of the axis of the moon. This is all we should be looking at, is we're looking at it from the top of the orbit. That your first diagram where it was not moving, all this did was it revolved around until it got back to the same state where the man on the moon is on the right and the far side of the moon is on the left. That defines a rotation in this frame of reference.
But from the frame of reference of the Earth, which I think the speaker is using, right and left are reversed with respect to the northern and southern hemispheres. I mean, the right, for example, in the northern hemisphere is east, and it's west in the southern hemisphere. So that's, I think, where the essential problem is. He's looking. He's not dismissing the Earth. He's looking at it from the point of view of the Earth.
But this diagram is looking at it from a different perspective, which is looking through the axis of rotation from the top orbit.
I have an idea.
I mean, is that the difficulty?
I'm going to ask if you can't reframe this problem. We got two separate systems working here. One is the inertial system, and the other is the spatial geometry. And the inertial system is responsible for the spatial geometry, but it's irrelevant here. You could take a point on the moon and a point on the Earth, and if you plot it out, you're going to get, in space, you're going to get a sine wave for each. And then where those sine waves intersect will give you the spatial system and the relative positions of the Earth and the Moon. And that should make it all clear. No?
That didn't help me. Did it help anybody else?
Can I come in on this just for a moment? I think that, I wonder if the problem is the little red line that goes through the moon, as it extends beyond the moon, there's a small tag sticking downwards. Well, when it's at the beginning of the revolution, right at the top, that little tag would be seen by someone standing on the Earth. By the time it's gone through to the bottom of the diagram, that little tag is still pointing downwards, but of course that would not be seen by somebody on the Earth.
Yep. Well, I mean, that's the problem here, that I think we obviously all agree what's going on in the diagram. But does that mean that the moon is or is not rotating? Or how many times did the moon rotate in this diagram?
Twice.
I mean, the bottom line for me And once again, I'm overstepping my boundaries as a moderator, but I'm just telling you my opinion. and even I'm entitled to my opinion that, the paradox which is set up in this is that this is claimed to be a single rotation, that this is what would happen if the moon rotated only once. And then we are shown the other diagram where the moon is locked to the surface of the Earth, and that is also claimed to be a single rotation by the mainstream. And so those two cannot be true at the same time. Both of those cannot show a single rotation of the moon. So I would say that what's wrong here is the claim that there is only one rotation going on in your animation, that there's actually two rotations going on there, not one. And that's why the pictures are different, because in one case the moon is rotating twice. In the other case, as mainstream would say, it's only rotating once, as opposed to zero rotations. Because I think, someone mentioned that everything that you call two rotations is one rotation, everything you call four rotations is three rotations. So logically, what you see as two rotations looks like one rotation, and what we see as one rotation looks like zero rotations. And that's why you think it doesn't rotate, because you've done this. You subtracted one full rotation out of the whole system.
So then how does zero rotation look like? Can you show me zero rotation? What is zero rotation?
Well, I think zero rotation is what you show as a single clockwise rotation.
No, that's
not
what
zero.
You show. It is rotating. You can see it rotating.
This is zero rotation. That is zero rotation.
You can see all the sides of the moon. How can it be zero rotation? All the sides of the moon are visible from the Earth.
No, I think zero rotation.
This is zero rotation.
It is rotating once
where the moon doesn't move at all. If you just take that image and just move it along the periphery of its orbit without moving it at all in absolute space, if you like. So in other words, the line will always be vertical, the red line. That would be.
If I could grab hold of this moon with my pointer and just move it anywhere I want, then obviously yes, it would show every single side to the Earth, but yet it would be completely motionless. I mean, it doesn't matter what side it shows to the Earth, right?
What if we were standing on the moon and we were using the stars to calculate the amount of times it rotated per orbit? How many times would we calculate that it rotated based on looking at the stars and using them to determine whether we were rotating as being on the moon or not?
Yeah, in this case, it would be zero. Like if all these little icons here were the stars, and the YouTube red and all this other stuff were the stars, and we were to, count out, how many times it rotates, we would have to conclude zero.
But you have to use the diagram that correctly depicts reality, which is the diagram labeled zero rotations, but relative to the stars, we would rotate one time.
Yes, I think relative to the stars, as observed on the moon, for example, or as observed outside the unit, the Earth orbit system, what we've described is correct. It would be one revolution for the norm, and 2 and 3 and so on. In other words, one more than the speaker says. But I think the speaker has postulated an observer at every point on the Earth's surface, simultaneously looking at the moon overhead. And if there's such an observer, well then, when it gets from the North Pole, let's say, to the South Pole, it has only moved half of its surface. So we're observing the opposite surface. The man on the South Pole observes the other half of the moon from the one that the North Pole man does. So he concludes that it's only half a revolution. So that's basically, I think, where the paradox is. he's sort of postulating simultaneous observation of the moon overhead by different observers on the Earth and what they would conclude.
All right. Well, we've had a couple people speak, but I want to hear what other people think. For example, Jim, do you have a comment? I think we've teased out all of the relevant points here. So I'd just like to hear what people have just been listening think. Jim, or maybe Clive, or...
What is the whole point of this? I came in a little late.
Okay, so the whole point is that our guest speaker is claiming that the moon does not rotate.
And what does that prove?
It proves that mainstream is wrong. See, mainstream thinks that the moon rotates once on its axis, and that's why it shows the same face to the Earth. So, our speaker here has written a book, and
it's just a, I mean, I still don't get the point.
Well, the point is that mainstream is wrong, right? Isn't that what we're here to always say, that mainstream is wrong? So, I mean, that's a pretty strong claim, that the moon doesn't rotate, right? Because the mainstream thinks that it does.
It's all just a question of your frame of reference. With respect to what? With respect to the fixed stars, I think it's pretty obvious that you're right, Franklin.
That rotates once, so the speaker has not been convincing to you that the moon doesn't rotate.
But I mean, even if I still don't get what we're trying to.
Well, we're trying to. I mean, obviously, our speaker believes that it doesn't rotate. So, I mean, we're discussing. This is a very controversial standpoint. So, we're giving him his chance to express his views, and we're just sitting here debating it. And that's what we do here in the Science Chat. We find controversial issues and we debate them. So that's what we're doing. So it doesn't mean that, a lot of times people point out is that we're arguing about things which are completely wrong. A lot of probably someone wandering in from mainstream would go, this is the silliest thing I've ever heard of. But maybe it's not.
Hello, Franklin.
Yes.
Hello, Franklin. Yes. I think yes. I think there is a fact. The fact is that the face of the moon, as seen from the Earth, is always the same. This is agreeable to both the mainstream and what the speaker is saying. The mainstream explanation is that the moon rotates and is locked with the Earth, but the speaker is saying there is no rotation at all, and that is why the moon always has the same face towards the Earth. So I think the observation is the same, both mainstream and the speaker. The explanations are different. I hope the speaker agrees with what I'm saying.
Yeah, I mean, I think the explanation of, say, the moon being locked to the Earth by, say, a gigantic bar, right? And then if you think of that, the moon just being, locked into that position, that you would probably say that since the moon cannot spin independently of the Earth, that you could say that there's no spinning going on because it can't spin. That was an interesting point. Now, I don't particularly agree with that, but that is one way.
What is your proof that the moon is spinning?
Well, I guess, like I said, if you had a sensitive instrument, you could put like a Foucault pendulum on the moon, and using that, you could determine with absolute certainty whether the moon was spinning or was stationary.
Okay. Has that experiment been done?
I don't think so.
If it has not been done, then we cannot rule out what the speaker is saying.
I mean, it could be that the entire universe is centered on the moon, and then, of course, then it's not spinning at all.
No, that's not what I'm saying. I didn't say the entire universe is centered on the moon. I said the observational fact is that the moon has always the same face to the Earth. Now, the mainstream explanation is that the moon rotates, but the rotation is locked to the Earth's rotation so that we always see the same face. The speaker is saying the moon doesn't rotate at all, and that's why we see the same face of the moon. Both of them are trying to explain the same phenomenon. It has nothing to do with the universe. And you have said no experiment has been done to prove that the moon is spinning. So how do we rule out what the speaker is saying?
If we're looking for proof that that the moon rotates, we could use a camera on the moon and watch the stars, and the camera would confirm that the moon rotates while orbiting.
Yes, I agree, but that experiment has not been done.
I'm sure that we have had cameras on the moon.
No, I think what we have are mirrors. Mirrors that are used to reflect laser beams from the moon back to the Earth, not cameras.
Well, we've had cameras on the moon and we've had people on the moon.
Yeah, I think for lunar navigation, this is what is often done, is that they reference the stars in order to navigate the Apollo spacecraft to the moon. And so definitely by that observation alone, you know, the Apollo astronauts know that the lunar surface is moving relative to those stars in what would be a consistent rotational period. I don't think anyone would disagree that from a star to
Yes, I think you have a point there. I think the speaker should investigate further and do more research. We have lunar laser ranging data, and maybe probably from there you can be able to determine whether there's any sign of rotation when those beams are reflected back to Earth, or whether there's no rotation. I think that is a possible area where data can be mined for more information on this issue.
I mean, it's an interesting point because, you know, I think one of the things that the speaker points out is that, you know, these ideas are so ingrained into us from birth that we don't even start to question, you know, things like, does the Earth rotate? We don't really even think about it. But, you know, the speaker makes us think. I mean, we've been talking about this for almost 2 hours, you know. Making various different points, so I have to say that it is by far not trivial, at least.
Okay. I also posted some questions. I don't know whether the speaker has anything to say about them. I typed in some questions.
All right. Well, let's see what your questions are. We're getting time towards the top of the hour, so let's end it with your questions here. So the questions: 1, will you prefer space is filled with XXX to space is like YYY? So this is actually not related to our moon question.
Okay.
Yes, but in the invitation to watch the chat, you showed us some videos and you said we could ask some questions. So in that one of those videos, the ether was discussed, and that's why I posted those questions. I want to know, does the speaker prefer space being filled with elastic substance, or will he prefer to say space is elastic substance?
Hello.
Let's see here. Did you want to answer that? And it doesn't really have anything to do with our moon thing, but it has to do with your second video, which is your ether video.
Yeah. No, I feel that space itself is elastic. It is filled with elastic. Yeah.
There's a confusion using the word filled and is. So if you say space is the elastic substance, I'm satisfied with that. But when you say space is filled, it means space is a different thing entirely, like a container, and you now pour something else inside it. So if you say space is the elastic substance, I'm satisfied with that answer.
All right. Well, actually, I mean, there were 3 videos, and really we've only actually done one of them. So I'm thinking that we could do another 2 conferences on the remaining 2 videos easily. So I mean, Habib, would you be willing to come back and do another conference on your video on the ether?
Yeah, definitely.
All right, because we're kind of at the top of the hour, and I've got a hard stop today. So, I mean, to summarize, we've been talking with Habib Mohanlal, and I did put a link to his book in the chat, and I'll see if I can bring that up. But he's done a lot of work, and we've only discussed one of his ideas, which is the idea that the moon doesn't rotate. So we've had a lot of discussions about perspective and geometry, and what does it mean to rotate, and how is there experiments you can do? Is it relative to the stars? Does it have something to do with centrifugal force? And all of these issues over a question that mainstream has settled definitively in their own mind. But like I said, we've been sitting here talking about it for 2 hours, sometimes very excitedly. So I don't think it's something that we can dismiss. So there's something to think about. So I hope that you've been able to help the speaker because I think a lot of these objections would be commonplace, and work on providing explanations to overcome those. And I think as dissident scientists, that's one of the things that we're really interested in doing, is understanding how people are understanding our theories and how we might better explain them. So, but that will do it for this week's version. Like next week's, we could possibly talk about his second video, which is about the ether, and I think you can ask more questions about how space is made out of, which is another interesting question. But I believe that will do it for today's conference. Let me see if I can just quickly share that link to the. There's a lot of things here. So this is Akimbo's. This is his book, The 7 Deadly Misconceptions. Here, so there you can buy it in paperback for $11.99 or Kindle $2.99, and you can actually look inside it and see some of the pages. So if you're interested in his work, you can look there, buy his book. That's one thing we always like as distant scientist people, reading our stuff. So I invite you to do that. But that will do it for this week, and I would thank our speaker. And like I said, next week, I think we can go over one of his next videos. But that will do it for now.